So hi all. So this video will be an overview of what I'll be going to take, and it will only contain about the high level view of the entire project. And I would like to first, say that there is assembly that you need to know. There is make file is a script. Okay, so it's a script file that you will require to run this project. So I will give a brief introduction about that. And assembly is very important over here because what does a compiler do? A compiler will compile down your high level language into a low level language. So a low level language doesn't mean it's a machine code, it's zeros and ones. So it's a step above it. So above it, as in like, see, your target machine would be like your laptop, or it might be an Android device, or it might be a edge device, say like your smartwatch or your earphones or your this headset, this like the headphones I'm wearing. So these would be the target devices. So based on the target devices, you have your uh, based on the target devices, you'll have a architecture within it. So that architecture will have assembly, right? Assembly. So, like for example, in our case, we have NASM, right? So it's x86. So it's a family of 8086. So if you look at 8086, so let me just show you what I'm showing. So you might have come across this, right? Microprocessor and microcontroller, this one. So you will have these segment registers, and you will have this this AH and AL combined is the AX register in 8086. This BH and BL combined is BX register. CHCL combined is CX register in 8086, and so on. So in 8086 you have 16-bit of register. So this AH and AL is divided, right? AH meaning the higher bit and AL meaning the lower bit of EX register. So here you have 16-bit register, right? So this is extended to your current laptop. Your laptop is 64-bit architecture. So instead of AX, you will have RAX. Okay, let me show you. 64-bit is what I was talking about. If you look here, if you compare this, if you compare this with this, see this AHL is the same thing here, AHL. So in 32-bit, it is EAX. In 64-bit, it is RAX. So similarly, you have RBX, just like your BX, which is divided into BH and BL. So the same thing, you'll have RAX, RBX, RCX, RDX. Okay. So this your 64-bit registers, which you will have in your current laptop. Okay. So laptop will have its own architecture. Similarly, your ARM process, right? ARM process. So our processor will have this kind of structure, right? So wait, process. So yeah, ARM process will have this R0 to R15 registers which the user can use. So that way you'll have a target architecture. It might be an ARM processor. ARM processor is, it's a RISC kind of architecture, and your x86 8086 is a CISC kind of processor. It's a CISC as in complex instruction set computer, and RISC as in reduced instruction set computer. So I believe most of my audience is from a computer or electronics background. For computer students, they have this subject called computer organization and architecture. So they would be familiar with RISC and CISC. But if you are not familiar with, just comment down. I'll make a small video about what's a RISC and CISC. Or I could just, paste a resource on what's RISC and CISC. I think that would be better. Okay. So based on your architecture, you have different assembly, right? Based on architecture, you have your assembly. So that's what I'm saying here. Uh, let me come back to here. So for example, this is my input. This is my input high level language. Okay. This is my high level language, which is my input. Now, my system will not understand this. So for it to understand, it'll compile down to this assembly language. So this was the RX register I was talking about, which is the 64-bit register. Okay. So now this 60 here is for your exit calls. Okay. So here RTI is again a register in 64-bit architecture. Okay, in 8086 it's DI register. In 32-bit it is EDI. So this is 63, right? For exit, RX register will be set to 60 and RDI is set to 3. So here this 3 is the argument that we'll set. So for example, if I had exit 100, okay, if I had exit 100, so my RDI would be set to 100. Okay, so let me just show you what it is. So currently 60 and 3 is there, right? So let me just change this one to just Spark. Okay, and yeah, I'll be using WSL because all these libraries, right? This make and GCC, all that it will work uh, perfectly with WSL. Okay, so if you look at now, this changed to 200. Similarly, if I change this to say 123, okay, so this will change to 123. This will change to 123. So what I'm trying to replicate here is this one. If I do gcc dem.c, so I'll get the a dot output binary from gcc. Okay, and if I run this one, echo this one, right? I'll get this one to three. So now if I change it to say 200 and compile it again and run the binary and run this, I get 200. So that's what I'm trying to replicate here. If I do right now, okay, let me uh, put it back to what it was, 100. Okay, okay. Now, in my case, my output is dot generated instead of a dot out. So if I do generated, okay, and if I do echo, so what should we expect? We should expect this 100 coming out. Okay, so 100. So if I again do this instead of this one, if I say, if I do 2, 3, 4, yeah. Now if I compile and run the instead of a dot out minus dot generated. So if I run this and run the echo, I should get 2, 3. So 2, 3, 4. This is what I'm replicating here. This functionality I'm replicating here. Okay. So this is the overview of the entire project. Right? So if I run this, okay. See, when we have multiple exit statements in C, the first one gets executed, right? The very first one executed gets executed, and we return out of the program. So in this case, if you look at this, the first exit statement that should get executed. So if you look at it's int x, okay. See, in my case, the simple table, I have a simple table. I combined syntax and semantic. Okay, let me continue with this and I'll go through the syntax and semantic process, how I did, so that you get an overview right now, and later on you'll understand like what I did, as in how this index is stored onto the simple table, like I told just now. So how's that process being? Okay. So right now, just understand that there is this space been allocated for x in our simple table. Okay, and that x will have a default value of 0. And then here A is being allocated as space and its default value is 11. As in the first value is 11. Then now X gets 11. Then it is 0B10. So it is binary 10 as in 2. X is 2. Okay. Then Y is X plus 2 into X is 2, right? 2 plus 2 into 3, 6. 6 into 2. 6 twos are 12. 12 plus, okay, let's write it down here, right? As in, firstly, first exit will get executed. So all these are gone. All these are dead code. Okay. And next, here x equal 0. So this line is done. Then here a equals 11. So that line is also done. Then we have x equal to a. X equal to a. So x will, so this is my simple table. Okay. Simple table gets updated here to x equal 11. Then again x equal to 10. 10 in binary is 2. Okay. Then again in similar table y is being created. Y is equal to x 2 plus 2 into 3 into x. What is x? X is 2, right? So this one should get evaluated, right? The we have this precedence operator, right? 2 into 3 into the multiplication has more precedence over addition in C, right? So my language is replicating C. So if you look at this gets updated as in 4 threes are 12, right? 2 into 3 is 6 into 2, 12, and then this gets evaluated. So y is 14, right? Now finally here we have 0, 7. 0, 7 is octal. So 7 is 0, 7 is 7 itself. Okay, in octal. So we have y plus 0, 7, which is 14 plus 7, which is 21. And now 21 divided by this binary now. So binary 111 is 7. Okay. How? Let's see. Uh, we have 111, right? If you look at this one, the lowest one, 1 into 2 power 0 plus 1 into 2 power 1 plus 1 into 2 power 2. So this portion is 1. Okay. Plus this portion is 2. Plus this portion is 2 part 2 is 4. Okay. So 4. So 4 plus 3 is your 7. So similarly, for your octal, instead of this 2, it will become 8. Similarly, see, for 111 in decimal, how will be 1 into 10 power 0 plus 1 into 10 power 1 plus 1 into 10 power 2, right? So what is it? 1 plus 10 plus 10 power 2 is 100, right? So that's how we get this one, right? So similarly, in any base, just put the base value here. If it's base 2, it's 2 power. If it's base 10, it's 10 power. So this is 7. Okay, so back to our thing. It was 21 divided by this value is 7. So divided by 7 equal to 3, right? So that's why if I run right now, so 3 gets assigned to RDA register. Okay. Let's look at one more example. Let's look at let's look at this. So here we have int a equal to 40, all of this. So here we have blocks, right? See, whatever is within the block, whatever is defined within a block, its lifetime is within the block. Outside the block, it gets destroyed, right? In C. So this the exact thing I did in my language too. So here if you look at this int a equal to a. So is a defined already? Yes, a is already defined. A is equal to 40, right? A is equal to 40. So this a is now 40, right? And this x equal to 3. Okay. And y equals 0 right now. Okay, let me not write this way. Uh, Let me write like this. A global equal to 40 is initially created in the single table. Then a block. See, it's not been made like this, okay? In how I did is like this entire for this entire scope, I have a simple table. Then within that, I have the block, right? So I create another simple table for just this block. And when this block is done, it is being destroyed. That simple table associated with that block is destroyed. Similarly, I create a new simple table for this block. And when this block is done, I destroy that simple table as well. Okay. So, so within it, it's not defined as a global or something. It's defined as a itself. Okay. So for just our understanding, I'm right now taking as a block. So this a global will be in its own symbol table, and this a block will be in its own symbol table. Okay. So let me do that, right? So that you will be more you won't be confused. So global, so let me name it as global symbol table. And within that global symbol table, I have A equal to 40. Okay. Then block symbol table. So here I have again A. Now A is equal to this A. So this A will be reference to this. It will see previous symbol tables about it. So it finds that A is equal to 40. So this 40 gets assigned. Okay. Then within it again we have okay, before that we have x equal to 3, x equal to 3, and y, see, by default I'm setting variables as 0. In my case I'm setting by default as 0. So y equal to 0, z equal to 0. Uh, Then again we have a block. So I'll name this as block 1 symbol table, block 2 symbol table. Okay. Now this block 2 symbol table, we have p equal to x. P equal to x. Let's see where is x. Okay, x we have x equal to 3, so p is equal to 3. Okay. And we have exit a. So what is a? A is 40, right? So we have to get exit of 40. So right now if I run this is test7.tc, right? So if I run test7.tc, so 40 is assigned to RDI. Okay. And this 60 will always be assigned because exit will assign 60 in RX register. So if I run here our generated and our echo, we should get 40. Okay. Okay. So you are getting an overview right now, right? This is the overview of my project. Okay. Of my compiler, how it looks. Okay. So now I have to see there are other stuffs here like this syntax tree. Okay. So what all phases do we have in a compiler? Since this overview, I'll not be going in depth. Okay. I'll make each section for each video section for each, like for Lexer, a particular video syntax tree, particular syntax and semantic. In my case, syntax and semantic is combined, so I'll take combined one because I had combined it. So that'd be the longest one because it has many concepts. It's combined, right? So it'll take more time. So first we have Lexer, right? Then after Lexer is where we tokenize. Then we have our syntax, but in mine it is syntax plus semantic. Okay. Then we have our code generation, which is our last ASM which we create, right? So syntax is creation of a tree and plus semantic. Semantic is like right now we did this example right of this A. Is it really defined? So if I remove this right, it should be undefined. Okay. Now if I run this, it should say A is undefined. Okay. At this line 3, A is undefined. These are semantic. So that A should carry a meaning at this statement, right? That meaning is bought by this semantic. So how this achieved by our symbol table? Okay. So in syntax we do not deal with symbol table. In semantic we deal with the symbol table. So since I have combined both, so we have to look at syntax and semantic. So syntax, how do I create? So firstly, what is syntax? What is syntax? Say in assembly this is the syntax, right? See this move should be followed by register and register or constant value. So let's not go by this. Let's go by our high level language itself. Okay. So see what syntax. Syntax here is see this is declaration, right? What is declaration? We have int followed by our variable identifier followed by the semicolon. Or we could have declaration this way as well. Int followed by identifier followed by the equal to operation assignment operator, then the int literal, and then the semicolon. So this is exactly what I had done over here. If you look at my grammar, so this is where your grammar, the theory of computation, which most of you would have had in your, I think in your second year or first year, who might have gone through this subject, CS people. So this is your grammar. So first we'll have a program. Okay. Then from program we have statements. And from statements you'll have block statement. Block statement was what? This one, right? This your block. This your block. This also your block, right? This also block, right? So this block. Then we have else. Else statement. So in my case, else I combined with from else I'll derive if statement, else if, and the else block. Okay. So this one I'll cover in detail in the syntax plus semantic phase. Okay, this grammar and how I created each of this part. Okay. Then followed by then add this code generation. So in code generation based on the tree which I generated. Okay. So based on that I am generating this. So this F right. Okay. F printf. Okay, into the file. So this 60 was which I told, right? This 60 for the exit call, and this RTI is the value that we'll get from our program, the argument that we sent. So that's why you can see that I am taking it from the node. So from the node I am taking the value. Okay. So I'll tell this. I'll run through the code in detail, right? This stuff I'll run through in detail. Okay, so since this overview, I had to first I want to start with overview, since you need to understand like what we're dealing with, the overview of what we're dealing with, so that then you can go step by step what's within it. So step by step, we'll go through all these Lexer. We'll go through this Lexer syntax plus semantic code generation, right? So in Lexer, I'll talk about how these tokens were created. See, I have these tokens being created. So int is a token, x is a token, this semicolon is a token. So all this I'll walk you through the code and explain each see, main thing is you shouldn't look at the code. You need to look at the ideation. So when I explain this, you should be in a position to write your own code by say C++ plus plus or some other language, right? So the ideation is the main part here. So that ideation will work, and so that you can build your own this same replica you can make in say CPP or say Rust, or even you can do it in TypeScript as well. So if I walk you through the ideation of how I did, you can make your own stuff, make your own kind of compiler. Okay. So I'll walk you through that process of how I thought and how the thought process of how I did the tokens. Then from tokens, how I moved into this syntax tree. Okay. In syntax tree also, there is this concept of this binary tree and left child right sibling, which I cover when I'm talking in the syntax space. Okay, that I'll walk you through in detail. So this what I had to cover. Okay. So then thank you guys. Then I'll upload with these phases. Next, I'll upload with Lexer, syntax plus semantic, and then last code generation. And as I told, I'll be pasting in this CISC and RISC, also this 8086 and x86 related stuff. So you can go through and understand what all this, what I meant by the target architecture and assembly and all those stuff. Okay, right. Okay, then we'll end this right now. We'll start with Lexer. No, sorry. Before Lexer, I did mention, right, uh, that I wanted everybody to have exposure to assembly. So I need to cover assembly and I need to also cover it. So after this assembly and make, we'll move to Lexer, right? Because I need to bring that into picture first, because these are like the basics which need to be covered. After that only we can to the next stage of Lexer and all those stuff. So after this assembly and make, which are like prerequisites which you need to know, after that only I can move to Lexer. So I'll make a video dedicated to this assembly, and then next dedicated to make, and then I'll make this video dedicated for Lexer, then syntax, semantic, and finally code generation. Okay. So okay, we'll see you in next video.